Muhammad Nabi, graduate student in Virginia Tech CBAS Lab, and first of all, I'm very pleased for having me here in the OCB Global Summit. I hope you like my presentation and find it useful. And basically, my topic is on 3 kilowatt power supply design with easy manufacturability, and this power supply is intended for the 48 volt bus power architecture. And so the legacy 12 volt power architecture included UPS unit to supply the power during the energy shortage, and also the 12 volt supplies the power to the electronic load through a 12 volt bus, which could have high dissipation loss at higher power. And recently we are more interested in the 48 volt power architecture, and with this one we will have less distribution loss in the bus, and also we can save the power loss in the UPS unit, since the battery bank here is connected directly to the 48 volt bus. And this system is also an ecosystem which is good for data centers and telecom application. And our focus here is fabrication and manufacturing of the DC stage with good efficiency and also high. And there are multiple topologies on how to design this DC stage, the 400 volt to 48 volt. One interesting topology is the three-phase interleaved LLC converter, and this topology is very good from conduction loss point of view, since the parallel multiple half-bridge LLC converters, each phase only handles 1/3 of the power. However, current solutions run this converter at 100 kilohertz, and they use lead wire magnetics, which is very complicated and more labor intensive, and also expensive solutions. And the other topology is to go with the fundamental single phase full bridge LLC converter. However, in this topology, there is a change where a single transformer is required to handle all the output power, 3 kilowatt power, and this will increase the conduction loss in the transformer and the output rectifier, namely the SR devices. So instead of using a single transformer for this topology, the single phase full bridge LLC, we can break down one transformer into multiple transformers in matrix transformer configuration, and each transformer here will only handle a fraction of the power. And this will reduce the conduction loss in the converter as well as the conduction loss in the output rectifier. However, a change here when we go to matrix of transformers, we basically increasing the number of transformer cores, and this will increase the size, and we can face this problem by increasing the switching frequency up to 1 megahertz, and this will reduce the size of the transformer. Also do magnetic integration, which will further reduce the transformer size and make the fabrication process much more easier with PCB winding transformer. And here's how to integrate 4 transformers into one matrix transformer core. So basically, when we look at the first 2 transformers, we can use a UI core for this transformer, and each leg of the UI core is basically one transformer with perfect interleaved primary and secondary windings. And for the second 2 transformer 3 and transformer 4, we can integrate them the same way. So basically, this is a solution where we have a matrix of 4 transformers using 2 UI cores. And then to make the all transformers are symmetrical, and we can here integrate the 4 transformers, basically integrate the top plate and bottom plate of the 2 UI cores into one 4-leg core. And this way we can guarantee good symmetry in the reluctance of the core for the 4 transformers, and guarantee symmetrical operation for the 4 transformers. And you can we can see here the flux distribution in this core will be going, the flux will go from core 1, core 3 to core 2 and core 4. And here we're showing the finite element simulation for the top plate and the direction of the flux. And we can further reduce the core loss in this transformer by changing or swapping the transformer 3 and transformer 4. Basically, we change the location of the transformers, and this will redistribute the flux in the core plates. And now we have much uniform flux distribution with less flux density, and this will reduce the flux density in the core plate and reduce the core loss in the matrix transformer. And furthermore, for this LLC converter for the 48-volt power architecture, we need to regrade the output voltage from 40 volt to 60 volt according to the battery charging profile. And for the LLC converter, we need to have a resonant inductor to get this regulation capability for the LLC converter. I mean by resonant inductor, significant resonant inductance value. So here I'm showing the PCB implementation and winding structure for this matrix transformer on 4-layer PCB. And here also, this is how we integrate inductor with the transformer. So in order to integrate inductor, we can extend the primary winding to wrap around one extra UI core, and this UI core basically enhance the leakage on the primary side and increase the resonant inductance value. And by doing so, we can get significant resonant inductance value and get regulation capability. And furthermore, we can also integrate the inductor core with the transformer core into one 6-leg core. And this 6-leg core is basically comprise the transformer and inductor in the same core. Also facilitate the fabrication process, since now we have one magnetic entity. And we can see here also with integration, we reduce the flux density in the transformer and reduce the core loss. And for this concept, we built a prototype to demonstrate the operation for this one. You can see here, this is the PCB structure for the whole converter, including the magnetic part for the transformer and inductor. And we use GaN devices for the primary and SR devices. And this is the integrated 6-leg core for the transformer and the inductor. And here, for this prototype, we show the efficiency of 97.3%. And furthermore, we can also integrate the inductor with the transformer in a different way to further reduce the footprint of this prototype and increase the power density. So here is a integrated 6-leg core. And we can see here, this is the winding current. We can see here at the center between the 4 transformer, we have a small current density. And this is basically underutilized part of the footprint. Also, when we look at the flux density in the core, we can see here a very small flux distribution at the center between the 4 transformers. And basically, regarding the flux and current, we can see here underutilization for the current and flux as the center. So, and the motivation here is how to use this area to integrate inductor instead of using 2 extra legs or 1 extra UI core. And for this solution, as we are discussing, extra footprint for the extra UI core is used to integrate the resonant inductor. So, so this is the first approach, the 6-leg core. And as we said, we can, instead of using an extra 2 legs, we can use the center area between the 4 transformer to integrate the inductance, the resonant inductor. So the second approach is remove the UI core. So we end up with only the transformer with 4 legs, and then add additional center leg between the four transformers to increase the leakage of the transformer and use it as resonant inductor. And if we can make this approach work, this will increase the footprint of the reduce the footprint of the transformer and increase the power. And basically, this is a two-step solution. First, design the core with 5-leg core. The second step, it change the winding structure to create leakage in the center leg. So here, this is the original winding structure for a perfect transformer. And to create leakage in the center leg, we need to relocate the secondary winding or primary winding to create this leakage. And here we only relocate the secondary winding so we change the windings between transformer 1 and transformer 2. Also, we change the winding between transformer 3 and transformer 4. And this is basically create unbalance between the transformers, and this unbalance will cause the mutual flux to reduce and increase the leakage flux. And here, this is a 3D like picture of how the 5-leg transformer looks like. And for this modification, we only used one extra 5th leg at the center between the all transformers, which utilize unused area between the 4 transformers. And for the modification in the transformer, we use exactly the same primary winding, so we don't change anything from the primary winding point of view, and we only swap secondary windings without adding any extra winding or termination. So here summary for my work. Basically, we have our target is to design easy to manufacture 3 kilowatt converter for the 48 volt bus architecture, and we have we use the topology of full bridge ALC converter, and we have 2 methods to integrate resonant inductor with the transformer. And basically, you are using matrix transformer to reduce the conduction loss in the converter and increase efficiency. And the 2 approaches include a 6-leg core structure and a 5-leg core structure with much less footprint and higher power density. And the future work here is to optimize the 5-leg core structure and compare between the 2 approaches from efficiency and power density point of view. At the end, I like to thank you very much for having me here in the OCB symposium, and I'm looking forward for discussion on my work, and please, if you have any questions, please contact me. Thank you.